The cosmos has just offered humanity one of its most extraordinary gifts. For the first time in history, the James Webb Space Telescope has delivered a crystal-clear, high-resolution image of an interstellar visitor known as 3I/Atlas. This isn't just another astronomical photograph. This is a window into another star system, a glimpse of material that was born light years away and has now wandered into our cosmic neighborhood. The image represents a turning point in how we understand the objects that drift between the stars, and it raises profound questions about the nature of our galaxy itself. Interstellar objects are among the rarest phenomena in observational astronomy. Until recently, astronomers could only theorize about their existence. These are bodies that do not orbit our sun, that originated in distant planetary systems, and that travel through the void of space on trajectories that bring them briefly into our view before they disappear forever. The first confirmed interstellar object, 1I/Oumuamua, arrived in 2017 and sparked intense debate with its unusual elongated shape and unexpected acceleration. The second, 2I/Borisov, followed in 2019 and appeared more comet-like, behaving in ways astronomers could more easily explain. Now, 3I/Atlas has become the third recognized visitor, and thanks to the James Webb Space Telescope, we are seeing it with unprecedented clarity. What makes Webb's achievement so remarkable is the level of detail it has captured. Previous interstellar objects were observed primarily through ground-based telescopes, which are limited by Earth's atmosphere and the technology available at the time. These earlier observations provided enough data to confirm the object's interstellar origins and give us basic information about their composition and trajectories, but the images themselves were often little more than blurry streaks across star fields. With 3I/Atlas, everything has changed. Webb's infrared instruments, operating from a stable position beyond Earth's atmospheric interference, have delivered an image that shows not just a dot or a smear, but an actual resolved body with visible surface features, thermal variations, and a faint coma of outgassing material surrounding it. The surface of 3I/Atlas tells a story of its own. The image reveals a patchwork of light and dark regions, suggesting a composition that is neither purely rocky nor purely icy, but rather a hybrid of both. Some areas appear reflective, likely indicating the presence of water, ice, or other volatile compounds that are sublimating under the sun's warmth. Other regions are darker, possibly coated with carbonaceous material or scarred by impacts accumulated during millions of years of travel through interstellar space. This diversity across the surface suggests that 3I/Atlas was formed in the outer regions of its home star system, where both rock and ice exist, and that it has survived a violent ejection process relatively intact. The coma surrounding 3I/Atlas is particularly fascinating. This halo of gas and dust is the result of volatile materials on the object's surface heating up and releasing particles into space. While the coma is not as dramatic as those seen around large comets in our own solar system, its very existence is significant. It tells us that even after crossing the vast emptiness between stars, Atlas still retains compounds that can be activated by solar radiation. This preservation of volatiles suggests that the object has spent most of its journey in the extreme cold of deep space, where temperatures are only a few degrees above absolute zero. In this frozen state, chemical processes essentially stop, allowing the object to act as a time capsule carrying pristine material from its birthplace. Webb's spectrographic analysis adds another layer of intrigue to the story. By breaking down the light reflected and emitted by 3I/Atlas into its component wavelengths, scientists can identify specific chemical compounds on the object's surface. Early results indicate the presence of water, ice, as expected, but also unusual organic molecules that differ from those typically found in solar system comets. These exotic compounds may have formed under different conditions of temperature, pressure, and stellar radiation than what exists in our own planetary system. The discovery of such molecules raises exciting possibilities for astrobiology, as it suggests that the building blocks of life might be distributed throughout the galaxy in varying forms, each adapted to the unique environment of its parent star. The size of 3I/Atlas is another aspect that sets it apart. Measuring several kilometers across, it is substantially larger than Oumuamua and comparable to a sizable comet nucleus. His scale indicates that Atlas is not merely a fragment broken off from a larger body, but rather a substantial object that managed to escape its home system intact. The ejection of such a large body requires powerful gravitational interactions, likely involving giant planets or close encounters with neighboring stars. The fact that Atlas survived this violent process and traveled across interstellar space without breaking apart speaks to its structural integrity and raises questions about how many similar objects might be drifting unseen through the galaxy. The trajectory of 3I/Atlas confirms beyond any doubt that it is an interstellar visitor. Webb's precise measurements show a hyperbolic orbit, meaning the object is not bound by the Sun's gravity and will never return. It entered our solar system from interstellar space, curved around the Sun under its gravitational influence, and is now on a path that will carry it back out into the cosmic void. This one-time passage makes Webb's observation all the more precious. Unlike comets and asteroids that orbit the Sun and can be studied repeatedly over many years, Atlas will be gone forever once it leaves our observational range. The window of opportunity to study it is brief, making every piece of data collected invaluable. Understanding the origin of 3I/Atlas involves tracing its path backward through space. Using Webb's precise positional and velocity measurements, astronomers can project its trajectory into the past and determine roughly which direction it came from. While pinpointing the exact star system of origin is extremely difficult due to the long timescales involved and the motion of stars themselves, scientists can at least identify potential regions of the galaxy where Atlas might have been born. Current models suggest it may have come from a star-forming region where planetary systems were still developing, and gravitational chaos was common. If true, Atlas represents a sample of material from a very different environment than our mature, stable solar system. The implications of Webb's observation extend far beyond astronomy. For planetary science, Atlas provides a comparison point that helps us understand whether our solar system is typical or unusual. By studying its composition and comparing it to local comets and asteroids, scientists can identify which characteristics are universal and which are unique to our particular corner of space. For chemistry, the exotic organic molecules detected on Atlas offer new insights into how complex compounds form and survive in extreme environments. For cosmology, the existence of multiple interstellar visitors in just a few years suggests that such objects may be far more common than previously believed, fundamentally changing our understanding of galactic dynamics. From a technological standpoint, Webb's success with 3I/Atlas validates the enormous investment and effort that went into building and deploying the telescope. Launched in late 2021 and positioned at the second Lagrange point, roughly 1,000,000 miles from Earth, Webb represents the pinnacle of observational astronomy. Its segmented mirror, measuring over 6 meters in diameter, collects infrared light with extraordinary sensitivity. Its instruments are cooled to temperatures just above absolute zero, minimizing thermal noise and allowing it to detect the faintest signals. The fact that this complex machine, operating in the harsh environment of space, can deliver such detailed images of a relatively small, distant object is a testament to human ingenuity and the power of collaborative scientific effort. The cultural impact of Webb's image should not be underestimated. For the general public, seeing a clear photograph of an object from another star system transforms the abstract into the tangible. This is not a computer simulation or an artist's impression, but a real image of matter that was formed around a different sun. That realization connects people to the cosmos in a visceral way, making the vastness of the galaxy feel more immediate and accessible. In classrooms, museums, and planetariums around the world, the image of 3I/Atlas will inspire wonder and curiosity, potentially sparking the interest of future scientists who will continue pushing the boundaries of what we can observe and understand. Looking forward, the study of 3I/Atlas is just beginning. Astronomers will continue analyzing Webb's data for months and years to come, extracting every possible detail about the object's composition, structure, and behavior. Computer models will be refined to explain how such an object could form, survive ejection, and travel across interstellar space. Other telescopes, both ground-based and space-based, will contribute additional observations from different wavelengths and perspectives. The collective effort will build a comprehensive portrait of Atlas that goes far beyond the initial image, revealing the full complexity of this cosmic wanderer. The discovery also energizes discussions about the future of interstellar exploration. While current technology limits us to observing these objects from afar, the possibility of sending robotic probes to intercept them is becoming more realistic. Several mission concepts have been proposed that would involve launching a spacecraft on a rapid trajectory to rendezvous with an interstellar visitor, collect samples, and return them to Earth. Such a mission would be extraordinarily challenging, requiring precise navigation and propulsion systems capable of matching velocities with a fast-moving target. However, the scientific payoff would be immense, providing direct access to material from another planetary system and potentially answering fundamental questions about the diversity of worlds beyond our Sun. The story of 3I/Atlas also highlights the importance of preparedness in astronomy. These objects are discovered only when they come close enough to our Sun to be detected, often giving scientists just weeks or months to observe them before they fade from view. Having advanced instruments like Webb-ready and able to respond quickly is crucial. Future sky surveys, such as the Vera C.